My name is Ipek Özkaya, and I'm going to be presenting our vision in next generation automated software evolution, which we're calling refactoring at scale. Lack of targeted design automation hinders software evolution. Redesigning and re-engineering existing software gets very resource intensive very quickly, and such re-engineering and redesigning tasks are not uncommon for industry software. A modest application with only 68,000 lines of code contains more than 10,000 nodes as well as 50,000 relationships. For a simple evolution task, a developer needs to understand what nodes to change as well as what relationships to resolve. And this gets very resource intensive without automated tool support as well as error prone. There is existing tool support for refactoring, even if limited. There is floss refactoring and root canal refactoring. Floss refactoring refers to continually tweaking a code base. Root canal refactoring refers to improving unhealthy code with infrequent but focused fixes. While we have some automated support, this support is typically integrated into the existing IDEs. They're developer driven, which means the developer needs to decide where to make the change and select from a given set of refactorings. What we're calling refactoring at scale provides a third category where the developer triggers the change. However, they're not necessarily in charge of it all. The tool provides fuller automated support by recommending different alternative changes along with different refactoring operations, and more importantly, takes advantage of current advances in search-based techniques. If we step back and look at some of the tools of the trade, we see that visualization and analysis actually is not uncommon in software engineering tool support. There are commercial tools that provide some limited assistance to assess the current state of software. Most of these tools are categorized as tools to assist understanding refactoring opportunities. For example, there are dependency analysis matrices that help you to understand where the software might be tightly coupled, or graph structures that again help you to understand why the software might be coupled. While these tools are very helpful in navigating and browsing the software, they typically treat the software code as homogeneous without providing support in terms of where you might actually focus your refactoring efforts. They typically focus on improving a quality metric rather than focusing on the call, again, such as isolating core for deploying as a service. There are refactoring assistant tools as well. For example, a lot of IDEs incorporate a subset of Fowler's refactorings, for example, Eclipse. But as I said earlier, these kinds of refactorings tend to focus on more floss or root canal refactorings. There are research tools such as JDividend that those of you who are in this research area might be familiar with that do provide refactoring assisting along with improving code. For example, JDividend helps to resolve feature envy or code clones with refactoring support. While these tools have their places, they tend to treat a software goal as improving the quality rather than evolution. While one might argue that is a kind of evolution as well, it necessarily does not address, for example, if I need to upgrade to a new technology, what are the areas of the software that I need to change and how can I refactor the software for that specific goal? The gap that we identify and that we lay the vision for, we're referring to as refactoring at scale. This is goal-driven, where the goal is often to improve, is more often to meet a business goal rather than simply improve software quality. For example, harvesting software involves moving a feature from one context to another, reusing a capability, factoring out common capabilities as shared assets, decomposing a monolith into modular code, or isolating a feature to enable containerization, or replacing, such as providing better options from other suppliers, or removing proprietary license code. These examples are not uncommon in our industry, especially when there is new technology. These kinds of evolutions are actually part of the tasks of software developers and often get ignored because of lack of effective tool support or become very timely and error prone. If we look at the challenges for achieving refactoring at scale, there are actually a number of research opportunities that provide both a way forward as well as interesting research problems. For example, how do we characterize the project's specific goals? The goal in understanding refactoring at scale needs to start with the business as well as the developer. And the implications are developers and the goal-driven workflows should be implemented in our next generation tools. What part of such refactoring process should be automated is also not a trivial problem. Automation should move from, should start with addressing the common and known problems, such as what are the dependencies, and identifying the dependencies and presenting those to the developer, but move from the tedious repetitive tasks to more complex ones, such as how do I refactor a database schema or stored features. And a big aspect of whether these kinds of refactoring tools are acceptable or not, as earlier work has identified, is whether these tools are acceptable to developers. Developers will need to adapt to these new workflows, as well as will need to be given confidence that the tools actually provide the solutions that will help their goal. Developers also will need to adapt to design decision-making with Pareto optimal solution space, where the trade-offs take priority rather than getting to one close to complete solution. A key underlying problem in this is what kind of a representation enables successful refactoring at scale. We need to be able to collect information from different sources and generate extensible representations to enable that information to be housed so that we can support both dependency resolution, database schema resolution, as well as dynamic dependencies that we can capture and resolve in the process of evolution. And most importantly, the developer workflows will change. We're more used to these iterative, local and smaller scale interactive developers, especially driven by the IDEs. These kinds of next generation tools will be more decision assistants, where you can actually provide the goal at hand. Maybe the tool runs and provides you a slew of solutions, and the developers select from those slews of solutions. And it will shift the time spent from design from problem discovery to routine solution generation, and implementing those solutions, as well as testing them after those selections have been made. So if I step back and demonstrate what is feasible today, I'm going to give a teaser of some of the work that we're conducting at the Software Engineering Institute's Architecture, Design, Analysis, and Automation group. We're adapting search-based optimization algorithms to recommend refactorings that can isolate software towards this harvesting or replacing capabilities. The input to our algorithms are a project-specific goal. For example, I would like to isolate this capability as a microservice, and obviously the source code. The search-based algorithm runs on the code and with the scope of the project specific goal, and comes up with refactoring recommendations. The underlying approach relies on a graph representation, where we extract the nodes and the relationships that we can exercise some of the fitness functions on. We formalize refactorings, mostly the ones from folders, but we go through different variations of these. For example, move method has several variations that you need to take into account, from a simple minimal viable move to a very complex one where you need to resolve multiple aspects of the semantics. And the fitness functions, it might change from an evolution or replacing this capability might say, well, I would like to optimize the code that changes, or I would like to optimize to run minimum unit tests, or I would like to make sure that I resolve all the dependencies. Depending on the goals and the fitness function, the search algorithm provides different solutions. The goal to achieve the success, let me rephrase. Enable to achieve success, we need to reframe the evolution problem. We're more used to analyzing software, looking at all the dependencies or all the quality issues that might be wrong and suggesting fixes. However, when we reframe the problem, we're focusing on only those dependencies that are relevant to the goal and that interfere with the goal, and resolving those. That actually helps us more achieve 80-20, as well as achieving success in the automation. It scales the problem down, as well as it helps developers to focus on what they would like to achieve, rather than being overwhelmed with the maintainability problem of evolution. If I demonstrate the flow, we start with the complex software. The example on the very left, the blue blob, is actually an actual software example with over 1 million source lines of code. By looking into the actual relevant software evolution task, we look into where we need to do the evolution. So it's only the portion of the software that is relevant. So by generating the problematic couplings by relationship type, we start with, in this particular scenario, about 2040 problematic couplings, but we reduce them to only a couple dozen that are relevant to achieving the goal. By using the multi-objective genetic algorithm, NSGA2, we generate a set of parity optimal solutions where the developers might actually look where their solutions might rest. And based on these solutions, select and implement a solution that suits their recommendation, which is a list of refactorings that they can actually follow. And these refactorings can be scripted to help with automated evolution in the long run. The refactoring recommendations create a sequence of refactorings that provide clear directions for the developer, independently reviewable, especially when we look into the acceptance of the developers in terms of implementing these changes. And they are built on refactorings that are already supported in development environments. So their actual implementation in code become more trivial, as well as provide future potential to automate application of the refactorings to code. Here's an example of our work in progress. And the developers we talked to actually resonate a lot with these kinds of tools because they can see if I want to achieve a reduction of the problematic couplings from at the very high end to the lower end, I need to only execute these handful number of refactorings. Hence, my task becomes less overwhelming and more manageable and controlled, as opposed to being overwhelmed with all kinds of nodes and elements that I need to touch. Looking ahead, the vision we lay forward is towards next generation automation for software evolution. We would like to develop automation that organizations can trust to provide accurate information for the kind of size, consequence, and resources needed for software changes. More importantly, we would like that automation to be focused on the particular task at hand, which often is more capability, functionality driven rather than quality and maintainability driven. And in addition, we would like to advance the state of the art to allow developers to sketch proposed changes, be able to at ease select between different alternatives, and move the automation problem to more of a design discovery rather than more of a mundane task that reduces quality fixes. If I demonstrate this on this little graph that we have, software typically evolves. There's an ideal design that you start with. As requirements changes occur and different environments come in, the ideal design evolves. But as software evolves through different bug fixes, new technology, functionality, and staff changes, there's a gap that opens. These kinds of next generation tools can help close this gap in a more controlled way and by providing the trade-off analysis as a tool along with refactoring support. With that, myself as well as my co-authors are happy to take any questions.